Hi, in this video I would show you a little project at which I worked recently. It's basically second version of something I made a long time ago. It's just some LED stripes attached to battery box with switch and boost converter on the back. When batteries are fresh, this is giving a lot of light, but it's not very efficient and batteries are running out really quickly. So I decided to make upgraded version of this. This upgraded version consists of a custom LED panel. These are 2835 LEDs. Most efficient that I found. They are outputting about 200 lumens per watt. This panel have 12 of them, are consuming about 2.4 watts and outputting over 400 lumens. Next is LED driver. It's made on IC PIM 2804. It doesn't need many complementary components, just inductor to capacitors and precise resistor to set LED current. It also supports PWM dimming and draw about 1 microampere of current when shut down according to datasheet. And last is not really necessary part, microcontroller to control brightness and show battery level. There for sure exists the detected IC to do this job of detecting button press and change brightness, but I didn't find any. Price PWM button controller IC in Google is resulting in DC-DC switching controllers. Here is the driver IC connected to power supply, and when I power it on, as you can see, LEDs lights up and are really bright, so I will flip this side. And as you can see, when I change voltage, driver is keeping constant power on LEDs. I choose slightly higher resistance than theoretically needed, resulting in smaller current than 12 times 65 mA per LED. However, on the final version I will probably put smaller resistor, so current will be bigger, because as I tested, LEDs barely heats up even on this thin PCB and at higher current than recommended. According to their datasheet, they can handle up to 160 mA, but efficiency is then lower and LEDs heats up more, of course. Currently, when I left it running for 1 hour, LEDs are reaching temperature of 55 degrees Celsius and driver of 50 degrees Celsius. It's hard to see on camera, but there is slightly drop on brightness when voltage is lower than 3.5 volts. Oh, here is more visible. I want to use 4 AA batteries as power for this project, so they will not have that low voltage anyway, but using this driver will be good for some high C rating Lion battery too. There is also a step-up version of this driver called PIM 2803 if someone is interested. For microcontroller for this project, I choose Atetiny 202 basically because I got some of them for cheap. Its job is not very complicated. It's in deep sleep when LEDs are turned off, drawing so little current that my chip multimeter shows 0. Press of button wakes Atetiny up and it starts generating PWM signal on pin connected to driver, currently for showcase this green LED. I didn't turn power supply. A single press when controller is turned off will resulting in 75% of visible brightness of LEDs, but PWM signal is about 57%. I set this option as default because it's most efficient. Every brightness level is gamma corrected, and next brightness level are 50 and 30%. When I press button next, it will turn off. Double press of button when controller is off is resulting in 100% brightness, or just set higher brightness level if it's already on. Long press will turn off the light at any brightness level. It's also measuring battery voltage, and if it's dropping below 1.05 volts per cell, a red LED indicating low power will light up. And below 0.9 volts per cell will start blinking. As you can see. I'm not implemented any forced battery protection. I mean something like forcing lower brightness at low battery or turning off. It will work until voltage is enough to keep the LEDs on and microcontroller on. ADC measure is updated once every 5 seconds because to achieve higher precision it's running on low frequency and collects multiple samples. According to PIM 2804 datasheet, PWM should have frequency of 500 Hz, so this is what I set in program. Sadly, it is generating visible flicking on some cameras. On oscilloscope you can see how duty is changing on different brightness modes. Here is 75% brightness and duty is 57%. Here 50% visible brightness is just 30% of duty, and about 50% of visible brightness is 8%, 9% of duty. And on full brightness, pin is just turned on to get rid of flicking. Here's schematic of final circuit. First of all, we got here battery input, because fresh 4AA batteries can have voltage higher than absolute maximum 6 volts for at a tiny. I use simple 2 diodes OC to drop voltage. Single diode might not be enough because at low current the drop is also lower. Next we have LED's driver. It's basically schematic from its datasheet. There are 3 resistors, but of course only 1 or 2 places will be occupied by them. I'm still not sure which one to use. Here are LEDs, nothing special. And then we have microcontroller with connectors and resistor divider to measure battery's voltage. Here I got PCB design. Front of the PCB is copy of my prototype design. Because I have opportunity, I added thermal bias at LEDs, but I don't think it's really needed. This side of PCB will be visible, so I made everything clean and symmetrical as possible. I think on 3D everything from the bottom will be more visible, but because at here, even if I turn off front copper layer, it's not really clear. Okay, here is the 3D view. So as you can see, on front we have only mounting holes, traces for LEDs and some traces that were required from circuit below. So here between these black lines there will be battery box. Here we got a driver circuit, and here we got microcontroller circuit. I'm not designing a case for this yet because I still don't have this battery container and I don't trust a Chinese dimension on pictures from AliExpress. But if it will be possible, I want to fit button and LED here, so this is why connectors are there. But if it's gonna be not possible, I'm gonna put it here where it will be less convenient. I want to show you current code too. It's not very optimized, but it's doing a same job and still fits into 2 kilobytes of memory. I will probably do some changes later if I will be bored, because there is still room to optimize. I written it all to be non-blocking and it's neat time-based, so I used RTC of at a tiny to get not very precise 1 millisecond tick. If everything were perfect, a tick should have 1.024 milliseconds period when RTC compare is set to 32. but internal RC oscillator is not very precise, so by experimenting I set it to 29. Of course, I won't gonna play around with every part like this. If I will want precise tick, I will use timer. Next we have here a state machine to determine button press type. Then some ADC functions and one file for all interrupts to keep it clear. When microcontroller goes sleep, it's changing his clocking source to a low speed oscillator, and I discovered that, well, on purpose, but still I can press buttons so quick that it will wakes up but not detect it in my program. And let's state off, and I totally stay on and use power when it seems that it's turned off. You can read it here. So that's it for this video. In the next part I plan to show the PCB assembly and case design, so click subscribe. Goodbye, and I hope my English not hurt you.